Okay, so today we're going to start 8.3. 8.3 really has to do with kind of what we did in 8.2, but now we're going to look at proportions versus means. So 8.2 was all about how do you find the average weight, stuff like that. Now we're going to look at what's the average proportion, so like p hat. So consider the population of M&Ms. Suppose you want to learn about the distribution of colors of these candies, but you can afford to take a sample of only 25 candies. So here I have a sample of 25 M&Ms. These are from a Halloween batch. So instead of red, we have orange, we have green, and we have purple. So there's 25 of them. So for the orange, there's 8. For the green, I have 9. And for the purple, I have 8. So I just took them from a big batch of Halloween M&Ms and grabbed 25 of them at random. So let me push these off to the side. I don't really need them anymore. So my proportions are, so it's everything out of 25. So 8 out of 25 is 0.32. And then 9 out of 25, 0.36. So some of this is from a different kind of M&M, so we're going to have to change some of the questions here. Let's focus on the orange ones, I guess. Is the proportion of orange candies among the 25 you selected a parameter or statistic? Remember, a parameter is the whole population, a statistic is the sample. So this is a sample, so it's a statistic, and it's p hat. Remember, p hat is your sample proportion. In the book, though, they just use p, which is kind of weird. Is the proportion of orange candies manufactured by Hershey's process a parameter or a statistic? So here's where you have a parameter. We use p for the population proportion. Again, your book will use pi. That's why it's my favorite book. So we use p hat and p. The book uses pi and p. So again, the parameter is for the whole population. Statistic is just your sample. So do we know the proportion of orange candies manufactured by Hershey's? No, especially since this was a Halloween version, so I don't really know what it's supposed to be. Do you know the value of the proportion of orange candies among the 25 that you selected? Yes. Do you suspect that every student in the class obtained the same sample proportion of orange candies in his or her sample? So if I passed out a bag of 25 candies to everybody in class, do you think they would all get 0.32? No. Remember we talked about sampling variability in the beginning of chapter 8. You know, samples will vary from sample to sample. So use the axis below to construct a dot plot of the sample proportions of orange candies obtained by every student in the class. So I don't have this because I'm doing this by myself. But what should end up happening is if we're looking at orange, if they're all even, it should somewhat be clustered kind of in the 30s and 40s. Maybe a couple people got the same number. Maybe somebody got a little bit less, but the majority should be all within between 30 and 40 if it's truly a third of each color. So that would be kind of what a sample would look like. Did everyone obtain the same number of orange candies in their sample? What should happen is this should be a no. Not everyone would get the same one. Not everyone's going to get 8. Some might get 9, some might get 10. Identify the observational units and the variable being measured from unit to unit. So this is kind of a throwback to chapter 2. Our observational units would be our orange M&Ms. The variable that we're looking at here, though, is the proportion of orange M&Ms. So if I were to comment on the shape, center, and spread, what should happen is the shape should maybe be approximately symmetric, because it should look a little bit like a bell curve. Our center should be somewhere, like I said, in the 0.32 or 0.33 range, if you're thinking 33% for each one. And then the spread, I'm just going to estimate it at 0.1, because the majority, like I said, should be between 30 and 40. If every student were to estimate the population proportion of orange candies by the proportion of the candies in his or her sample, would everyone arrive at the same estimate? No, again, that's sampling variability. Make a conjecture about the population proportion of orange candies. So, the population proportion would be similar to the average of our sample proportions. Again, assuming each student had access to only his or her sample, would most estimates be reasonably close to the true parameter? Would some estimates be way off? No. There still would be outliers, depending on how you took your samples, but the majority would or should be close. In what way would the dot plot have looked different if each student had taken a sample of 10 candies instead of 25? So if I only gave you 10, and each one, that means you might only have 3 or 4 of each. Your dot plot would end up being more spread out. We kind of touched on this at the beginning of Chapter 8, because you're going to have more variability. In what way would the dot plot look different if you had a sample of 75? Here again you have less variability. So the bigger your sample size, the less your variability. Is it easy to calculate the value of a sample statistic? Yes. What about the value of the population parameter? Not unless you have Google, and you can look at these up. So what's the primary goal of sampling? So this is a big thing for second semester. You want to reach conclusions about one or more characteristic of the population from which the sample was selected. Okay, that's our big goal for second semester, is to reach a conclusion based on a sample. So what does sampling variability mean? The variability in the value of a statistic from sample to sample. Okay, that kind of just helps us reiterate sampling variability, this whole example. So now let's look at kind of what proportions and how they differ from means that we did at the beginning of Chapter 8. So, in addition to trying to discover the mean of a population, statistician also seeks to discover the proportion of individuals in a population who possess a certain property or characteristic. So for example, we could have P be the proportion of U.S. residents who approve of President Bush, or the proportion of Salem High School students with at least one AP class. Unfortunately, without conducting a census, we never get to know the true value of P, the population proportion. Instead, statisticians will estimate P by taking a sample and computing the sample proportion, which is P hat. Again, this is P with a hat on top. So it's the number of successes in the sample X divided by the sample size. So X is the number of successes, X is a binomial random variable. So let's suppose 22% of registered voters in California are senior citizens. If we were to take a random sample of size 100 and find the sample proportion of senior citizens, or P hat, what values might we get? Well, you never know. You could get 0.22, you could get exactly what it says, you could get something higher, 0.27, you could get something lower, 0.18, you really could get anything. Something kind of close, maybe not too crazy. So what the distribution ends up looking like, the shape should be approximately normal, because we're going to talk about that central limit theorem again. Our center, which is now mu of P hat, should stay the same, about 0.22, whatever your actual P value is. The spread, this is going to be the tricky thing, and it's going to come kind of down here. Sigma of P hat will be the square root of 0.22 times 0.78 divided by 100, the whole thing. And I'll explain why in a second. Oops. So divided by 100, square root, all that, 0.041. So underneath is kind of our general properties for proportion. So kind of just like we did with the means. The mean of P hat is the same as the population mean. The standard deviation is P times 1 minus P over N. These are also on your formula sheet on that back page. So for one population, P hat, mu of P hat, sigma of P hat. So right there. So we were using these two. Now we're up here using these two. When n is large and p is not too close to 0 or 1, the sampling distribution of p hat is also approximately normal. Here's our check. It's not as simple as just n's got to be greater than 30. N times p has got to be greater than or equal to 10, and n times 1 minus p has to be greater than or equal to 10. So then it's safe to use our normal approximation. So these are the ones that we have to check. We can't just have n is greater than 30. So it takes a little bit more, but it's not too bad. And then our last one on the back, this just kind of tells you how the mean and standard deviation were created. Again, you don't need to know this, just know the final p, and p times 1 minus p over n square rooted. So let's try an example. So suppose that 43% of registered voters in Michigan are Democrats. What's the probability there will be less than 30% Democrats in a random sample size 50? So first thing we want to check, is it okay to use a normal approximation? So we're going to do n times p has got to be greater than or equal to 10, and n times 1 minus p has got to be greater than or equal to 10. So the thing that is annoying is you have to do this. Before we could just say, oh, n's greater than 30, we're good. So you want to look at, though, your actual p value. This is p, this is p hat. Okay, so we got to look at that 43%. So 0.43 times 50 has to be greater than or equal to 10, and 0.57 times 50. I'm doing this in the wrong order. That's okay. Has to be greater than or equal to 10. So 21.5 is greater than or equal to 10, and 28.5 is greater than or equal to 10. So it's safe to use a normal approximation. So it's safe to use what we've always been using. Okay, so now I'm actually going to do the problem. So we're trying to find, so off to the side I'm going to find mu of p hat. Again, that's going to say 0.43. Sigma of p hat is now going to be 0.43 times 0.57 divided by 100. Where did that? 0.05. Oh, not 100. 50. Maybe I did something wrong. 0.07. There we go. Okay. Mean standard deviation. Now, we're looking at the probability that p hat is less than 0.3. So, I'm going to do this one by hand, and we'll use the calculator on the second part. So, I'm going to find the probability that z is less than 0.3 minus 0.43 over 0.07. So 0.3 minus 0.43 divided by 0.07. So z is less than negative 1.86. So formula sheet, negative 1.86, 0.0314. So about a 3% chance. Which is not, it kind of makes sense. If it's 43% is your true value and you get 30%, sort of makes sense. What would happen to the probability if we increased n? So we sort of talked about this before, but we really only did it with an in-between. Remember, the bigger your sample size, the less variability there is. So if this is my lower sample, so let's say this is 50, and this one's 100. I'm looking at a less than. If I'm looking at less than this number, I would have that area. But if I go here, less than that same number gets me a smaller area. So actually, if we increase n, the probability will decrease. Since there is less area under the curve. Remember, standard deviation will increase as n increases. No, standard deviation decreases as n increases. So you have less area under the curve. So what should happen, we're going to now increase our sample size to 100. So what should happen, this probability should get much smaller. Now, should we check that it's n times p, it's safe to use a normal approximation again? It's pretty easy because we're going to do 100 times 0.43 should be greater than or equal to 10, and 100 times 0.57 should be greater than or equal to 10, which is 43 and 57. So it's safe to use a normal approximation. And just get used to doing this. This is going to be one part of what we're going to do second semester, so it's kind of used to just getting used to that. So now our mean is 0.43. Here's where the standard deviation is what I did before. 0.43, 0.57 divided by 100. And you end up with 0.05. So now this time, let's just use calculator. So, normal CDF, negative infinity to 0.3, 0.43, 0.05. So lower bound, upper bound, mean, sigma. So negative a bunch of 9s, oops, 0.3, 0.43, 0.05. So now we have a probability 0.0047. So obviously you can tell that it decreased because there's less area under the curve. So sort of the same thing we've been doing with means, just our standard deviation is slightly different and using the central limit theorem is slightly different.